So welcome to this video on what we can do with transformers in a network. Specifically, what we will see today is how we can use PyTorch to train our own decoder-only GPT transformer to detect anomalies in configurations in the network. And these are configurations on routers throughout the network. We'll focus today on anomaly detection in VPRNs, and we will also speak very quickly about what these transformers specifically are. I don't intend to turn this into a lesson on transformers. There are wonderful sources that I will provide links for that will help you understand how these transformers work. But specifically, my implementation of the decoder-only transformer stays true to the attention is all you need white paper that authored and inspired transformers. And so what we will see is a GPT transformer in action, learning patterns in our CLI configurations, including anomalous patterns in the network. That's what makes this implementation so powerful. And we will see during inference that the transformer is able to correct anomalies that existed in the network. And so what you will see here in our CLI, and this is, we'll see this in action in a few minutes, is we've got a misconfiguration on this specific VPRN, and this VPRN has been given a route distinguisher of 2.2, and you will see that the transformer learns that that is the wrong route distinguisher for this VPRN instance, and it is able to correct the route distinguisher value. So how does that happen? The transformer, using auto-regressive learning, is able to see patterns throughout the network and learn, in this particular use case, that the route distinguisher for this VPRN instance, VPRN1, must always be 1.1. And again, what is critical is that even though we have the VPRN misconfigured in the network and we trained with an anomalous VPRN, we have enough ground truths on routers throughout the network for the model to ground itself and correct the anomalies. This is a wonderful example of how we can use AI for intent-based networking, where the ground truth is in the patterns that are in the network itself. So how does a GPT transformer work? We spoke about auto-regressive learning, but before we even able to train, what is really good practice, and we've done this in this particular example and implementation, is we normalize the CLI. This is really important. We do this as humans. We need to do this as humans in order to be able to focus on what is key and filter out the noise. We do the same thing with the training corpus that we are going to feed into the transformer. Transformers love working with numbers, so we convert the VPRN CLI, which are really tokens in the world of machine learning and deep learning, and we convert those tokens into IDs. We create embeddings and add positional encodings to each one of these tokens so that we have vectors in the embedding space that stores important information about relationships between the different tokens in a CLI. This is a concept known as self-attention. And once the prerequisites are in place, we train. So this implementation was inspired by attention is all you need. And we know that the paper is practical, the paper is true, and so I made sure when I wrote the code that I wrote code that stayed true to the principles of this paper. And so what happens during training is, at the beginning, in very early stages of training, the model, the transformer, our AI doesn't know that RD22 is incorrect for VPRN1 and PE1. But as we go through multiple epochs and gradient descent, at the end of every epoch, we see a convergence of our weights, where our vectors specifically start to self-attend to create or to generate true relationships and help us identify what truly is correct and what is anomalous. And I'll show you in a little bit what that means. I implemented this as well in Python notebook, and we will see in heat maps the strength of the relationships between these embeddings. So what we expect to see when our training is complete is that during inference time, or when we are ready to detect anomalies in this network, the model corrects the incorrect route distinguisher with what was expected to begin with, the intent. Now, what we can do in a production scenario, of course, is, and this is best practice, is to, of course, involve the human to verify that this indeed is the correct configuration, and then we can go through the process of perhaps using agents to deploy the corrected configuration. So let's see this. Let's see this solution in action. So we're going to run our CLI transformer, and you'll see it happens. Things move really fast, and I found this fascinating in my work with transformers, because this is not a small corpora. I have VPRN configurations about well, actually exactly 10 on 10 specific PEs, and so we've got about 100 CLI configurations here. And what we did see is within the matter of seconds we trained, right, and we're immediately able to correct based on the patterns that the model has learned what the expected VPRN configurations need to be. And again, I want to bring your attention to the correction of this anomaly. We see here that after the model was trained, it was able to very successfully, correctly predict that the route distinguisher should not be 2, 2, it should be 1, 1. I hope this gives you a good understanding of what we can do with transformers, what we can do when we choose to use a different type of AI that aren't agents. And I hope you also have an understanding or an impression of how powerful this solution is. Now, I do want to shout out a couple of very important people who influenced my learning with deep learning. One of them is Javier Antic, who wrote a book on deep learning for networks that opened my eyes to what we can do with deep learning in this space. And Daniel Burke, he's an excellent teacher. If you want to learn about how to train your own deep learning models, I very much recommend him as a teacher. I will share the links to these resources and to these people in my write-up. Thank you for your time.